So we have this model being displayed over here in the Fluent setup, and you can see that in the version 2021 they have created a very good graphical instances to be displayed in the screen. This will help us to visually understand how your model is looking like. But maybe in the previous versions this kind of representation of the models is not available. Nevertheless, it doesn't impact the kind of simulation what we are performing. There are certain options over here which you can utilize, and we can turn off the shadows or the background floor like feature which is being displayed in the form of grids. So that will help us to simplify the visualization as well. All right, now the most important aspect of this simulation is the physics setup, apart from the meshing or the grid generation what we have done in the previous video. The physics setup will determine the simulation. It will determine the results what we are achieving. It will determine, help us to validate the solver with the experimental studies. Now in this video what I will be showing you will be a kind of setup which has been finalized after lot of study, lot of research, and lot of understanding from different aspects. Okay, now the final thing is what I'm trying to show you in this particular video. But in the background, when I was dealing with these kind of flows, I had to read plenty of papers. I had to understand what conditions are they using, what settings are they using, and what is the reason for that. So it takes a lot of time for finalizing the numerical setup as well. Okay, but in this video I'm directly showing you the final thing what is suitable for simulating these kind of flows. Okay, and there might be possibility, or there may be a possibility that the setup what you are aware of may be suitable for this case. So in that case, if you try to validate with your numerical setup, if you feel that I have done something different than what you know, then you can just try to validate with that, and if that is also happening, that is well and good. That is not a big problem. Okay, so in CFD doesn't mean that it always doesn't mean that one way is the right way. There can be another way, but it depends on your end results. The end results should match, should be it must be validated actually. Okay, you cannot directly claim that the settings what I cannot directly claim that the settings what I am showing you are correct. Okay, there might be a possibility that they might not be correct as well. Okay, so end of the day, the point is, the bottom line is, you have to choose the appropriate equations and solve them appropriately based on the model what you have, and try to compare your result with some reference data, and you can just prove the authenticity of your numerical scheme in that way at least. Because CFD is all about equations. If you are performing a job in real time, that is in physical experiment, then physically we can see what is happening. Okay, but here it is like with a single click you can turn on a kind of flow, with a single click you can turn off a kind of flow, right? So that is what is the best part of CFD, but you must know how to use them efficiently and appropriately as well. And that always happens with experience. Try to work on different cases, consider a case of your interest, and try to dig in, deep dive into it, work on different validations, comparisons, reading of different articles or journals, and you will be eventually gaining enough knowledge in your field of interest. Now, as my courses are oriented to different applications, I cannot dig in for specific application into much deeper extent. That will be impossible for me to do it. I have these projects being created. I have created these projects to give an overall brief and try to make you understand how to tackle different flow phenomena in CFD here. And before discussion of the physics setup for this kind of flow, I would like to show you something on the screen over here which you are probably aware of. So in general terms we call them as hot air balloon, and you must be knowing, or you must have seen this flying object in either real life or in your television screens or internet or any cartoons as well. Okay, and you must be if you have taken an interest to find out the functional principle of this particular hot air balloon, then you probably know that you will be having a kind of fire being displayed, I mean fire being generated at this position, right? So that will help us to you know take the hot air balloon upward direction. It gives a kind of lift to the complete object, right? So you must have seen in some movies or any cartoons or anywhere that if they want to move up, they turn on the fire and the balloon moves up, and if they want to come down, they just turn off it, so it falls down due to the action of gravity, right? So what are the two forces that are moving the object up and down? The first force is generated with the help of what do you call hot air, and the second force is with respect to the gravity. So these are the two factors that are influencing the variation of the movement of the object in the space. All right, now if you have your I may not be aware that you are aware of this thing or no, and if you're really aware, then that is really well and good. But what is happening when the hot air is pumped into the chamber of this hot balloon or this balloon, right? What is happening over there? So we know from the properties of air that the density of air varies with temperature. Okay, now if the temperature of air is hot or a higher temperature air, then the density is very low or lighter density, you can say. A lighter density implies less weight. Okay, so this is what is the relation. You have high temperature, that indicates low density, which indicates low temperature, and lightweight air tends to move upward. So this is what is the property of air. Okay, whereas on the counterpart, if you have air present at lower temperature, okay, in a cold state, the air will be denser. A denser air indicates a higher weight or heavier weight. A heavier weight indicates the movement of air in the downward direction, okay, because it falls down because of its own weight. So this is what is happening in balloon as well. We are trying to create a lighter air, okay, in the region of the complete balloon, and the surrounding air in the atmosphere is heavy, and it is normal weight, actually the normal density what we have in the surrounding atmosphere, but the density of air in the balloon is lighter. So as I mentioned, that the lighter weight or lighter density air moves upward, the air in the chamber is moving upward direction, and when it is moving upward direction, it is carrying the object which is connected to it in the upward direction. So this is what is happening over here. But you might be wondering, we were dealing with indoor environment and all of a sudden this instructor is wasting your time with the discussion of hot air balloon. But I have a reason for this. I am not really wasting your time. I'm just trying to make you understand the foundation of this, or the concept of this background of air densities. Okay, and now we will land up in the ANSYS manual. Okay, and we will see, I'll attach the link in the resources, so do not worry. When heat is added to the fluid and the fluid density varies with temperature, a flow can be induced due to the force of gravity acting on the density variations. So this is what is written over here. The density variations will try to create a flow, and not only the density variations in the air, the presence of gravity as well impacts the movement of the air, especially in our homes or indoor environments. Okay, and coming to this object, yes, if if you're turning off the fire, obviously the density of air inside will try to come back to normal, and it'll eventually come down, and also the impact of gravity from the earth's surface will pull it downward, right? Now the same phenomena is happening in the indoor environment as well. Okay, and such buoyancy driven flows are termed as the natural convection or mixed convection flows, and that can be modeled in ANSYS Fluent, right? So this is what is happening, and these kind of flows are basically called as density driven flows, or buoyancy driven flows we can call them, and they are termed as natural convection or mixed convection flows as well, right? Now when we are coming to the respect of indoor environment, okay, so you have this room over here, okay, and let me just pan or move the site, rotate the site. You will be having air entering from the inlet Okay, generally I'm talking about general way, forget about this boundary conditions of this particular experimental study. In general note, imagine your cool air is entering from the inlet. This is the inlet, it is entering into the room. Now the cool air is heavier because of its lower temperature, higher density. So the air tends to move downward and it falls down actually. Okay, it doesn't move upward to the roof or the ceiling. It falls down because of its higher density and low temperature, or heaviness in the air. Okay, so after it falls down, it try to moves along the direction. Okay, whatever obstacles are present in the domain, for example the furniture, the presence of humans, so that creates an obstacles in the airflow movement, and it tries to surpass the obstacles and just moves in one direction, in some direction, right? And eventually it exits from the exhaust. But what is happening in this thing is, the reason for it to fall down is also the presence of gravity. Okay, that is the first thing. Then we have its own weight, because of that higher density it falls down. Now what is happening is, if there is the presence of heat source in the domain, like I mentioned you, if you have any electronic devices running in your room, if you have occupants being seated in your room, okay, for example you're in a classroom, you have numerous students sitting in different locations, right? Maybe forward bench, the backward bench, the corner of the room, the front of the room, right? So all these are spreaded heat sources, we can say. Okay, if you have a television, that is a heat source. A laptop, a computer is a heat source. And imagine if you have your kitchen in your this particular room, then you have your cooking utensils over there which are being cooked, so that is a kind of heat source again, right? Now these heat sources, the surrounding air of the air surrounding these heat sources will take the temperature of that heat sources, and it tries to become or change its density, as it is mentioned in the manual over here, that when heat is added to the fluid and the fluid density varies with temperature, a flow can be induced due to force of gravity, right? So that is what is happening. The air which is surrounding the heat sources uh, changes its density, and when it is changing its density, it's becoming lighter in nature, in weight, and it is moving upward. Okay, so you'll be having, imagine a human is standing over here with a very there is a presence of lighting. Imagine a lamp is being added in the corner of the room, okay, standing lamp, and you'll be having a presence of some electronic devices. So the air which is surrounding these devices or electronic equipments or heat sources will be lighter, and it moves upward direction. As I mentioned you that the density of the air is lighter, so it moves upward, and when the air is moving upward, it hits the ceiling and again changes its direction, and it interacts with the oncoming air from here, and again you'll be having a kind of circulation being happening in this region, right? And the reason for it to come down is again because of the presence of gravity, right? And eventually in this circulation manner, a kind of flow field is induced in the room, right? And the flow field variation depends on the positions of your heat sources as well. So on general note, we never think into much detail whenever we are planning to set up our rooms, right? We don't really think where must be the inlet, where must be the heat sources positioned. If you're having a presence of continuous circulation happening in a room, then that will eventually create an air which is having an older age. That means it is staying in the room for a very longer interval of time, and an air which is staying for a longer interval of time will be contaminated, obviously, because occupants like us humans generate carbon dioxide. I mean, we emit carbon dioxide. Okay, not only that, we emit uh, you know uh, aerosols as well. Like for example, if a person is sneezing in the atmosphere, okay, so his particles move in the environment, and if we have some circulation zones which are quite risky, that will catch up, and that will make the contaminants stay in the room for a longer interval of time, and that will eventually be harmful for the humans again, right? So indoor environment is a really vast topic. You have to consider the engineers who are designated for these jobs, have to research a lot, especially in hospitals where the air has to be cleaner as possible. Okay, and especially at public places where you are encountering numerous people, and especially pandemics, it's very dangerous, right? So you have to be very careful with respect to the flow field in the indoor environment as well. Okay, I believe I've given a very intense introduction of the concept. So I'll take a pause over here. In the next video, we'll directly jump to the setting up, and we will see what all strategies being utilized for this simulation. So let us just try to catch up in the next video.